what were lambda and sigma?
Yeah, lambda is the line charge density, and sigma is the plane charge density. So lambda is charge per length. Sigma is charge per area. All right. Sorry. All right, so that's where we left off on with chapter 22, sorry. So now what we're going to do is we're going to do something a little different. We're going to take a look at this in terms of not forces, but energy. So we want to take a look at the work done by the electric force, because if you recall, the electric force is the conservative force. So we can calculate the work done by that force. The work done by any force is minus the change in the potential energy due to that force. Such as when you looked at gravity ages ago. When gravity does work, it loses the potential. So what we want to do is we want to take a look at what is that loss in potential. So if we do this, what we say is the work done by the electric field is equal to the integral from A to B of F dot dr, where dr is the line along which that force is going to be. Excuse me. So then we take a look at this, and I'm going to just put this in terms of the electric field itself. So let's say that we have an electric field E, and we have a charge moving from point A to point B. Charge Q moving along that line from A to B. So the work done from A to B is equal to integral of A to B. The force of the electric field is Q times the electric field dot dr. And so what we would say is we'd say that the work done, that the change in potential energy, the delta U, is equal to minus the integral. The Q could come out because that's the charge, from A to B of E dot dr. And this is how we look at potential energy when we talk about an electric field. If we do that by plugging in a point charge, we get that the potential energy between two point charges, say Q1 and Q2, and you could do the integral on your own. Have fun. Do the integral on your own. Take 2 point charges. The potential energy is 1 over 4 pi epsilon naught, that's our constant. Q1, Q2 divided by R. And that's with respect to infinity. That's with respect to infinity. Okay, now notice that a couple of things. First of all, there's a factor of R here, not R squared. R here, not R squared. You can think of it as one of the R's is integrated out. So one factor of R is integrated out, and you get R and not R squared. The other way to think about it is that energy is force times the distance, and so you're multiplying by one of the factors of distance here, and that's the other way to do it. If you still don't believe me, you can look at the derivation in your textbook.
The energy between
Two charges. This is the potential energy between two charges. Okay. Now the other thing about that potential energy is that it can be either positive or negative. Think of it this way. Remember that kinetic energy can only be positive. Okay, so if you go way back and you remember kinetic energy, and you will need this formula too, by the way, for kinetic energy. Remember what the kinetic energy formula is? 1/2 times mv squared, okay? So for kinetic energy, this can only be a positive number. It can only be a positive number because masses are always positive and velocities are always real. Because even if you said had a negative velocity, remember negative, that just indicates direction. And you would square that anyway, so it's going to be a positive number. The only way that it would be negative kinetic energy would be to have an imaginary velocity. So I suppose if I imagine something moving with the velocity, then it has a negative kinetic energy. Because I've imagined it, and it has an imaginary velocity. I still have my sense of humor, and it's still just as bad as it was last week. So. All right, so that's the kinetic energy. Okay, but potential energies can be positive or negative. And a lot of times, in the case of the electric field, they're positive and negative. Negative is just as likely as positive because the charges themselves can be positive or negative. So we don't have negative masses, but we do have negative charges. So in this case here, if you just look at the potential energy here, and this is with respect to infinity. So in other words, if I have two positive charges together and I let them go, notice that energy is going to spring them out to infinity. I'm going to have some energy, they're going to repel. So that's going to be positive. I'll put two negative charges, same thing. They're going to repel each other, I let them go, they're going to repel. If I put a positive and a negative charge, then I can't get those charges to move to infinity on their own. They're attracted to each other. So that's a negative potential energy. And in fact, if I have a negative potential energy, and I have to put energy into that electron to get it to move to infinity. Now, there are units of energy. But first we have to define something here. Because if I look at this equation up here, it's got a Q in it. And I want to talk about just the effect of this electric field on the region around it without actually having to move a charge. If you remember when you did mechanics, when you talked about the potential energy due to gravity near the surface of the Earth, what you had is you had a quantity which was mgh, where h was the height above the ground. You had this, and you put a boulder of mass m at that particular height. You plugged in the m, you calculated the potential energy, okay? But I could put a boulder of any mass at that height. Right, you know, so in other words, I wouldn't have to put that particular boulder there. So even though you didn't do it for the gravitational, we could have said, well, what if I wanted something to describe the energy in terms of just the mountain itself? Well, I want to cancel out that mass that I'm putting there. So what I could do is I would define a quantity that I took this and divided it by the mass. That way, it wouldn't matter what mass I put there. This potential energy per mass will describe the mountain itself. Describes the mountain itself. Everybody see how that analogy here. So this describes just the mountain. It's not energy, but it's related to the energy. We want to do the same thing with charge. We want to do the same thing with charge. We want a quantity that doesn't depend on the charge that I'm sticking there. Because this potential energy depends on what charge I'm sticking there. I want a quantity that doesn't. And so what we do is we define what we call electric potential as energy per charge. And so we define electric potential as being the energy, the electric energy, divided by not mass, but charge Q. Yes.
On the top, for your delta U, when you pulled out Q, why did it become negative?
Oh, because the work done by the work done is negative change in potential energy.
Oh, so W equals.
Yeah, W equals negative delta U. So when I put delta U down here, I have to put a negative sign here. Okay. So what we do is we give this quantity an actual letter here. We're using the letter V to describe that quantity. We talk about that letter V. Now, the letter V is the electric potential. Has a more common name. That's voltage. That starts with V. Okay? And so there's the units of voltage, which are what you think the units of voltage would be. Volts. The unit of voltage is volts. There you go. And a volt is equivalent to 1 unit of energy, which is a joule per coulomb. So a joule per coulomb is a volt. So by doing this, what we can do is we can say, well, okay, then the potential energy U is equal to the charge Q multiplied by the voltage V. And that would be with respect to infinity or with respect to whatever zero you choose for the voltage. When we talk about voltage, there's a term that we use for something that is where our V equals 0, where we have chosen V equals 0. And there's two ideas of this. One is that if we put something into the ground, what we say is that the Earth has so many atoms in charge that it can essentially avoid whatever charge I stick there and not change that potential. And so that we talk about the chosen V equals 0 in any type of circuit or anything that you deal with is referred to as the ground. And you can have positive or negative electric potential with respect to that ground that you've chosen. So anytime we talk about absolute potential, we always refer to it as with respect to some ground. Because a lot of times when we're doing the gravitational potential energy, we pick the 0 to be the ground. So we just kind of call this the ground of the electric potential. So V equals 0. And that's what we refer to. So if you hear the word ground, that means the place and everything directly electrically connected to that place has 0 electric potential. Okay, now let's go fix our fancy formula over here for the delta U. Because what we want to do is we want to say, well, if I didn't have a charge, I still want to be able to calculate my voltage just from what's going on with the electric field. And so we can go back and we can relate the voltage to the electric field, delta U. So from VB minus VA is equal to negative, the Q gets divided out, integral from A to B of E dot, and I do want to be a little bit, I'll change this in terms of, because your textbook says DL. Okay? I like this formula slightly better than the one that the book gives you. The book does one more thing to this formula. The book takes these two things and reverses them and gets rid of that negative sign. Because basically they multiply through by a -1 here. I don't like that. Because if I look at an electric field, let's look at a simple case of this. Your electric field is uniform. The electric field is uniform. And I want to go along a point, and I'm just going to go straight along that electric field. From A to B. And it's been a while since I've thrown some numbers at you, so let me throw a couple of numbers here. Let's say that the electric field is 150 newtons per coulomb, and that this distance here is 3 meters. Okay, 3 meters. That's good, right? 3 meters. Okay. There you go. And I move from A to B. And I move from A to B. So now, I want to figure out what the difference in the voltage is from A to B, which is why I like to say final minus initial. That's why I like keeping this side the way it is. Final minus initial. Integral from initial to final. So when you're reading the book and you see their formulas, remember, what are they calling final? What are they calling initial? I'm calling A initial and B final always. And I integrate from initial to final. So let's see what the change in voltage is. So VB minus VA is equal to negative integral from A to B of E dot dl. So that would be the integral from, if this is the x-axis, say that's the x-axis, right? So this would be the integral of 0 to 3. The E field is 150 newtons per coulomb, and it is along the x-axis. Dotted with my dl. My dl is just dx here. And by the way, it is along the x-axis. Now some of you can see where this is going anyway. Because in this case, the E is uniform. The E and the dl are parallel to each other. Everybody see that? The E and the dl are parallel to each other. So that could just come right out. This is just a long way around it. Okay? If you see a situation like this, you just say, oh, that's the electric field multiplied by the distance. Because what happens is when I integrate over the dl, that's just going to give me my distance. So this turns out to be negative 150 newtons per coulomb multiplied by 3 meters, which is negative 450 newton meters is a joule, divided by coulomb is a volt. So it's 450 volts. Sorry.
So 1 volt would be a force needed to move 1 coulomb of charge for 1 meter, right?
Well, a volt is the amount of electric potential needed. That if you put 1 coulomb at it, it would have 1 joule of energy.
Which would mean you can't move it for 1 meter.
But it's also it's the amount of voltage between 1 newton per coulomb electric field multiplied by 1 meter. It's actually defined as the electric potential, the energy divided by charge. That's how we define volt. There's a different equivalent unit we'll get out of this, by the way. Okay. So now, what does that tell you? If it's negative 450 volts, the voltage is dropping from A to B. The voltage is dropping from A to B. Okay. This formula tells you that if you move along the electric field you are decreasing your voltage. You're decreasing your voltage. If you move against the electric field, you're increasing your voltage.
Is that fact?
Huh?
Is that fact?
Yes. You move along the electric field, you decrease your voltage. You move against it, you're increasing your voltage. Okay? So that's why I like that negative sign in there, because that just reminds you that if you move along the electric field, you are decreasing your voltage. You're going down in your voltage. We can also talk about the voltage created from a point charge. So if I have a point charge Q, I can now talk about what voltage it creates, saying that with respect to infinity. In other words, V equals 0 at infinity. Far, far away from all charges, the voltage is equal to 0. And I want to know how much voltage is created. Well, now we can go back to our test charge Q naught. So basically we have a Q naught there that's not really there, but it's there. It's a mathematical trick that we use. The potential energy, this is the distance r, let's say, and let's go ahead and use our 4 pi epsilon naught, since your book loves it so much. Epsilon naught Q naught over r. So therefore the voltage would be equal to that potential energy divided by that test charge Q naught that I stuck there. So the voltage created by a point charge is 1 over 4 pi epsilon naught Q over r. Now, the cool thing about, in terms of calculating voltages, let's say that I have a -2 microcoulomb charge here, and I have a +3 microcoulomb charge down here. This one is 3 meters away from a point. And this one is 5 meters away from that point. And I want to know, what is the electric potential at that point? What is the electric potential at that? Okay. Well, what we would do is we would, just like we've done for electric fields and forces, I want to add the electric potentials contributed from each of those two charges at that point. So let's do it. So V2 is, just go ahead, that's KQ over R. So in other words, this is 9 times 10 to the 9th. My Q is -2 times 10 to the -6 divided by the R. The R is 3. So what I would get there is -6,000 volts. I think so, because 9 divides nicely into 3, and I get 3. 3 times 2, -2 is -6. Multiplied by those, 10 to the 9th times 10 to the -6 is 1,000, so therefore it's -6,000. It's -6,000 volts. Notice a couple things about it there. Electric potential can be positive or negative. Notice in this case, I'm not dealing with a magnitude and a direction. Voltage is related to energy. Voltage, therefore, is a scalar quantity. It's a scalar. It's not a vector. It's not a vector. It's just a number. I'm either at this voltage or I'm not. It's not 600 volts in the X direction, and no, it's 6,000 volts is what it is. Now let's do the other one. V3 equals KQ over R. 9 times 10 to the 9th. 3 times 10 to the negative 6 divided by 5. Can't quite do that one. 45 divided by, no, 27 divided by 5 is what? 5.4? Okay. So it's positive 5,400 volts. Or 5.4 times 10 to the third. By the way, when you're doing this, you'd use 8.99 and whatever numbers they give you, which aren't as nice and easy as the ones that I give you, but that's just so we have time in class to do a couple of days. Now, I want the total voltage at that point. What do? I just add the numbers. That's it. They're not vectors. There you go. That's it. Negative 600 volts. You just add the two numbers together. They're not vectors. Now let's go back to our map of the electric field. Our map for the electric field. Our old dipole map of the electric field. Now what I'm going to look at something is called equipotential surfaces. Or surfaces of equal potential. Now if I were to look at this, and I look at this formula here, this one right here. Let's say that A and B are to have the same potential, so that this difference would be 0. Well, either my E is 0, that would be silly, or I don't go anywhere, that would be silly, or what has to happen between the two? The angle has to be what? 9 degrees, has to be perpendicular. So your equipotential surfaces are going to be perpendicular to your electric field. So whenever you have, I draw an equipotential surface, it's going to be drawn in such a way that at all these points, it's going to be perpendicular to the electric field, and vice versa. And then one other corollary to this was that electric potential and conductors if I have a conductor in what I would call an electrostatic situation. In other words, the charges move and stop. They don't keep moving. That's a little bit different. But in a situation where you put some electric field there, the charges move and then they stop. This entire conductor is an equal potential surface, because inside of the conductor, after all the transients die out, E is equal to 0. Because if I try to put an electric field inside of a conductor, those charges can move. Those charges move, they're going to move until the electric field is 0. So what happens is that E is equal to 0 and the voltage is constant. So any conductor in an electrostatic situation where the charges are not continuously moving, you're going to have that conductor be constant. Voltage is going to be constant to the conductor. Now we can turn this thing around and get the other way. Let's go back to my voltage equation here. Here's my voltage equation. Let's say that I'm given the voltage. I'm told what the voltage is, and I want to find the electric field. Okay. First of all, let's do this for constant stuff. So for constant stuff, this would be delta V equals, if I pull the E out, minus E, and I pull the ds out, I'm going to just call this L. What I do is I could say that my electric field is equal to minus delta V over L. This actually gives us an equivalent unit for electric field. That's the same as the Newton per Coulomb we had before. So when we talk about the electric field, we can express it in two terms. We can express it as so many newtons per coulomb, or we can express it in terms of the voltage. It depends on the context as which one you want to do. If I'm asked about forces and stuff, I probably want to use newtons per coulomb. But if I'm asked about voltages and energy, I probably want to use this unit, which is the volt per meter. They're the same thing. They're not in different sets of units, they're both equivalent units. Now the other thing we do, if we do this more formally, for those of you who recognize this next formula, I will give it to you. How many of you recognize what this upside down triangle is talking about? Okay, a couple. It's the gradient. Electric field is the gradient of the electric potential. What it is. Those of you who don't recognize it, I'm just going to give it to you in one dimension. The x component of the electric field is equal to minus partial derivative with respect to x of whatever the voltage is. So if my voltage is equal to 4x squared, say, okay, in the x direction, that's my voltage as a function of x. So if it looks as a function of x, my voltage does this. Okay? I can find the electric field in the x direction at any point along that axis simply by taking the derivative with respect to x. What this little funny d thing is if I've got other variables in the derivative, I treat those as constant numbers. I won't do that to you because you're not, even though it's really logical and you should be able to do it at this point, I'll wait until you formally learn it Because if I had a y in here and I get to treat it as a constant, then I just pull it out of the integral. I just pull it out of the derivative. I don't have to worry about it. But we'll only do things like this. So it would be minus 8x. No, because e is negative. Negative. And I take the derivative. And so the electric field, if you're on the negative side here, the electric field is going to point toward here. If you're on the positive side, it points toward there. The electric field, remember, will always, there's another thing, point from positive to negative voltage. Actually, I should say different. High to low. Because it could be two positive voltages. And the electric field would still point from the larger one, the more positive one, to the more negative one. So high to low voltage, that's the direction of the electric field. All right, that's it. I'll take a look over the homework that I gave you and make sure that there's nothing that's too complicated. Please do work in your groups to get this done, and we'll discuss it on Monday when we come back. Huh? No. There's no group problem. I just want you to work in your groups on the homework itself. Yeah.
Yes, the bad news was that I called in, told her that I couldn't make it. I really wasn't feeling well. I'm feeling a little bit better today, even though I sound like this. So then they said they had a substitute. Don't worry about it. They had somebody to take the class. I have to worry about it. So I went home to sleep, and then I woke up later, found out that the substitute thought that the class was at 11 and not 9:30. And by the time anybody went over to tell them that, hey, there's a class going on, it's not 11, it was like 10 o'clock. So they decided to just cancel the class. So your class did get canceled on Monday. It was fucking, yes, that's what happened. So, and they told me to send an email, but I really wasn't feeling up to sending an email. My brain was just, really bad. So I just figured I'll come and tell you today that there was no class on Monday. So I'm going to adjust the schedule a little bit, but since I can't change the date of the test, because, changing the date of the test is kind of like, big no-no because people make plans around that kind of thing. So instead, if I don't get over all of chapter 23, then all of it won't be on the test. What I plan on doing is going over all of chapter 23, but doing it in a cursory way, leaving out some of the gory details that you guys don't really want to see me do, and lots of derivations that you don't want to see me do anyway. So that's that. So the test is next Wednesday. Yeah. Yes, there's a test next Wednesday. That's why I was like, whoa, that's not good. Yeah, you got 3 tests in the final here. So it's next Wednesday. And it's your first exam. Covers chapters 21 through 23. I'm trying to get you close to me today, by the way, just because I don't know if I'm still contagious or not. And I don't want to do that. I wouldn't wish this on people because I've been fighting it since Friday, and it just kept lingering and lingering and lingering. I'll probably be okay by next week, but it's, get my voice back kind of thing. But, yeah.
Do you want us to turn in?
Yes, please turn in your team problems now, so the team problems can turn in those now.
How's it going? What's up?
My goodness.
He's sick.
Come see me Monday. Yes.
the syllabus?
Yeah.
Put your name on there.
Yeah.
And the one thing, there is no team problem for chapter 23, because, you know, we have time to, I'm sorry, but still get together and work on homeworks and stuff like that, so. So please do that. All right, let's do it. Let's start out by kind of, we have a bit of a review. We started talking about way back when, force between two charges. I have two charges, Q1 and Q2, separated by distance, R12. The force between those charges is a K, Q1, Q2 over R12 squared. K is a constant, 9 times 10 to the 9th, Newton meters squared per coulomb squared. R12 is the distance between these two, yes.
Are we gonna get like a formula sheet or something?
Yes, I will give you a formula sheet that you're gonna have for the exam, so. It won't have all this nice stuff on it, but it'll have the basic equation. So what you need to do is you need to remember, you know, what this situation this is used in.
Yeah.
Okay, so this is force between two charges. Force between two charges. And I'll be nice, I'm even gonna give this one with a K in it instead of the 1/4 pi epsilon naught. But after this, I'll give the other ones with the 1/4 pi epsilon naught, the ones for the electric fields.
What about the constants? Are you gonna give
Oh,
us?
of course I need the constants. This is kind of, yeah. Here, so we have this, and then to find the direction of this, it's like charges are gonna repel, opposite charges attract. You have to remember that. Okay, remember that. Like charges repel, opposite charges attract. You can just remember that. Of course, you guys aren't old enough to remember the Paula Abdul song, that she did opposites attract. That's back when Paula Abdul actually sang, or she tried to sing. Now she just judges American Idol and sits there, looks pretty, and compliments everybody. That's what she does. Oh, by the way, I was gonna admit this on Monday, but I have to admit it today. It's my fault that, Carolina did not win that Super Bowl.
Why?
Because I understand perfectly why. You know, if somebody knocked the ball out of my hand and there's a bunch of people diving for it, there's no way I'm gonna go get it. No way. I'm a wuss, you know, I'm not gonna go diving down and get a ball like that. And Cam Newton, when he was doing that, said, well, what would Eric do? Eric, there's no way Eric's gonna get the ball, so I won't either. So that's what I did. So it's my fault. I'm not sure why Cam Newton was asking what I would do, but it just seemed that he did exactly what I would do in that same situation. And, you know, of course, I'm a middle-aged, wussy little guy that there's no way I'm gonna go after that ball. Maybe he shouldn't be asking what I would do, but for some reason he did, because I saw him do exactly what I would do. Oh, don't forget that. So, that's what happened, so it's my fault. Sorry. Lay on. My bad. All right. Then we talked about the electric field, and we had the force of a charge placed in an electric field. So this is one where we have the electric field already, and a force is there. So the force is equal to charge Q multiplied by the electric field E. So if the charge Q is positive, it's going to move along the electric field. If the charge Q is negative, it's going to move against the electric field. Then we talked about creating the electric field. And we create electric field by charges. Electric field from a point charge is equal to charge Q, got some point P, Q over 4 pi epsilon naught r squared.
Mike just died. Your microphone died.
It just died. Did it die? Is it dead? It's dead, isn't it? Is it dead now? Oh, good. That's a great, great question. Yeah. Yeah, so it's KQ over R squared, for those of you who like the K version better. Okay. The reason why I'm going to give this is because what we did is in chapter 23, then we extended this. Chapter 22, we extended this. We started talking about other configuration. Did it die again? Is it dying?
It might be low on the battery.
Well, stop being low on the battery. I gotta get a new battery second. Plug me something in. I wonder, ultrason, what kind of batteries are that? How about now? Is that better? All right, now hopefully it won't go die on me. Don't die. All right, now, so, and that's when we're talking about a point, yes. When we're talking about the direction of the electric field is going to point away from a positive charge and toward a negative charge. And then we went into the electric field from a line of charge, line charge density lambda, where lambda's charge per unit length. Magnitude of the electric field here is lambda over two epsilon naught r. I think that was right. I don't know whether it's 2 or 2 pi. So let me see. Ah, darn. It's 2 pi epsilon naught. So 2 pi epsilon naught r with just 1 r. And then for a sheet of charge, sigma, the electric field is just sigma over 2 epsilon naught, and it's uniform electric field. Is it dead again?
Yeah.
Why does it keep dying? Is it just like, why is it not wanting, why is it being mean to me?
It doesn't want you to teach today.
It does not want me to teach today, I know.
Go home, take a break.
No, can't do that now.
Rest your
There we go.
rivet.
All right, rest my rivet. Yeah. All right. All right, here we go.
Yes.
So, did it die again? Why does it keep dying? I swear.